Okay, so now let's look at how capacitors are connected in parallel. So I have 3 capacitors that are in parallel, and kind of thinking about how charges are going to get deposited on them. Again, we know that from the power supply, charges are going to leave the power supply and they're going to build up on the plates. So let's say I've got all these charges, they're moving along. They get to this point right here and it's a junction. And so we're going to have a split. So some charges are going to go here, some charges are going to go here, some charges are going to go here. And when that happens, when I have charges that get built up on this plate, charges are going to leave. So some of these charges are going to go, and these charges are going to go, and then these charges are going to get repelled. And so those charges get repelled off those plates, leaving these plates with a positive charge. So we see that for capacitors in parallel, the total charge from the power supply ends up splitting up. Now, if we think about voltage, remember that this would be the higher potential and this would be the lower potential. So anything that is connected to this line is going to be at the higher potential. It's going to be connected to the 12 volts. Anything that's connected to this line is going to be at a lower potential. So if I think about these plates here, down on the bottom, they're directly connected to that lower potential line. And these plates here are connected to that higher potential line. So this will be 12 volts and this will be 0 volts. So each of these capacitors ends up storing 12 volts of energy. So we see a similar relationship for the charges and the voltages for resistors and capacitors in parallel, in that the charge, the current splits up, but the voltage is going to be the same. So if we think about relationships for charge and voltages for capacitors in parallel, the charge splits up amongst the different paths. And if the capacitors are in parallel with the power supply, they will have the same voltage as the power supply. So in terms of the equation, the charge is going to split up, so my total charge is going to equal to the charge that gets deposited on the first capacitor, plus the charge that gets deposited on the second capacitor, plus etc. And then my relationship for voltage is that my total voltage that I have my power supply would be the same voltage that I have on the first capacitor, and it's going to be the same voltage that I have on the second capacitor, and on the third capacitor, etc. So again, let's look at how these relationships affect the total capacitance. We're again going to look at our equation for capacitance, where Q is equal to capacitance times voltage. And I'm going to take this relationship and plug it into this relationship here for my total current, my total charge. So instead of writing Q total, I'm going to write C total, V total. So I'd have C total, V total. Instead of writing Q1, I would have C1, V1, C2, V2, C3, V3, etc. But I know that voltages are the same in parallel, so that can actually just cancel, because it's in every term. So I would have that for capacitors in parallel, the total capacitance is just the sum of the individual capacitors. And again, we were kind of expecting that relationship. So in terms of what's similar, the relationship for charge current is similar to series or resistors, and the relationship for voltage is similar to resistors. But in terms of how the total resistance versus the total capacitance combines, they're opposite of each other. So I want to go through one example of just capacitors in series parallel to kind of make sure you have a basic understanding of it, and then when we get back to class, slide this. When we get back to class, we'll go through another example. So this says that two capacitors, C1 is 2.5 microfarads, C2 is 5 microfarads, are connected to a 12-volt power source. Find the charge on each capacitor and the total charge if they're connected in parallel, and then what are the Q values if they're connected in series. So let's just start off like in terms of what I know my total voltage is 12 volts, and I know I've got these two capacitor values. And my goal is to figure out what's the charge? What's the charge on an individual capacitor and what's the total charge? So let's start off by solving for the parallel case. And for the parallel case, I know that my total capacitance for capacitors in parallel is 7.5 microfarads because they just add up. Capacitors in parallel just add up. And then if I know my total capacitance, I know that this relationship is true. Like, well, I know that Q is always equal to CV. Okay, so I know that Q total is equal to C total, B total, and that would be 7.5. I'm going to leave it in microfarads because it would just mean that my coulombs comes out to be microcoulombs. So my total charge is 90 microcoulombs. Now, these capacitors aren't the same, so this is not going to get split up evenly. So to figure out how much charge is on each individual capacitor, I'm just going to apply this equation individually. I'm going to say, okay, well, Q1 is equal to C1 V1. So that would be 2.5 times, or let's just make sure I'm keeping my units straight, 2.5 microfarads times 12. So Q1 is going to equal 30 microcoulombs. And then Q2 is going to equal C2 V2. So 5 microfarads times 12, which is 60 microcoulombs, and that checks. 30 microcoulombs and 60 microcoulombs adds up to be 90 microcoulombs. So that is for if it's in parallel. So now let's go ahead and look at what would it be if it was in series. So I'm going to erase this, and if you didn't write this down, well, then you can just rewind the video and get it. These values stay the same, but how things combine is going to be a little different. So let's start off by, again, just finding the total capacitance. So for capacitors in series, they add up as inverses. So this would be 2.5 microfarads inverse plus 5 microfarads inverse. And when I do that, the capacitance in series ends up being, what did I get? 1.67 microfarads. And you can check that if you'd like. So that's my total capacitance. So I can use, again, this relationship. If I know the total capacitance, I can find the total charge. So Q total is equal to C total, B total, which is going to be 1.67 microfarads times my total voltage of 12. And that comes out to be 20 microcoulombs. Now, I know that for capacitors in series, the charge is the same. So if this is Q total, this is also Q1 and Q2, okay? Now, a way to kind of check your work is to see if you could figure out what the voltages are, because we know the voltages should add up to 12. So you could do the Q equals CV for each one. So you could say, well, 20 is equal to 2.5 microfarads times voltage 1, and 20 should equal 5 microfarads times voltage 2. So for voltage 1, you get 8 volts, and for voltage 2, you get 4 volts, and that checks to be my total voltage. Okay? Okay, so hopefully that gives you a pretty good understanding of capacitors in series and parallel. Again, when we go back to class, we will go through another example just to make sure that we have a pretty good understanding of capacitors.